Welcome to the Level 1 Fixed Income Summary video series. This video is a summary of the reading on understanding fixed income risk and return.
First point here is sources of return. The terminology here might be slightly confusing, but the concept is straightforward. I'll use the terminology from the curriculum and then explain what they are talking about. The total return is the future value of reinvested coupon interest payments and the sale price. So what this is saying is, let's say that you buy a bond at time 0, and let's say that this is a 2-year bond, which means that you get coupon payments every 6 months. So at the end of 2 years, or at the end of period 4, if you have reinvested all these coupon payments, at the end you will have the future value of these coupon payments and the money from selling the bond over here. Even if the bond has a longer maturity, but if you sell over here, then over here you have the coupon payments and the price from selling the bond. So that is being called the total return. Let's say when you do all this, over here you have $120 from selling the bond and from all the coupons that you received during the life of this investment. And let's say that the initial amount that you spent, the purchase price was 100. Then the horizon yield is the internal rate of return between the total return of 120 and the purchase price of the bond. So it's a fairly straightforward concept. It just boils down to IRR based on the cash flows. The 100 is your money spent, so that's the investment, and then 120 is the future value of all the cash flows. So the IRR simply connects these two numbers. That IRR is also called the horizon yield or the holding period rate of return. Sources of return. So now, building on what we've been talking about, the receipt of the promised coupon and principal payments on scheduled dates. In other words, one source of your return is simply all the coupon payments and the principal that you will receive. Then you reinvest your coupon payments and you get an interest on that. So that is also another source of return. And then potential capital gains or losses on the sale price of the bond prior to maturity. If you hold the bond to maturity, then obviously at maturity you will get par value. But it is possible that you sell before maturity, and it is possible that interest rates go down, which means that you will have a capital gain on the bond. The realized horizon yield is equal to the original YTM if coupon payments are reinvested at the same interest rate as the original YTM and the bond is sold at price on the constant yield trajectory. Now there are a couple of important points here. Let's understand the constant yield trajectory. Let's say that you buy a discount bond. So the example here is from the curriculum where we have a 10-year 8% coupon bond purchased at a price of 85.5 per 100 par. So obviously in this bond the market rate initially was higher than the coupon rate. So you bought the bond at a discount. But if you hold the bond to maturity, then the price of the bond will slowly go up to 100. So this point is 100. This line connecting the initial price up to 100 is your constant yield trajectory. If we connect this with FRA, you can think of this roughly as the amortization table, where we slowly change the value from the initial price and work up to the par value. So if the interest rates do not change, then we move up this constant yield trajectory, and that's why it's called constant yield trajectory, because assuming yields remain constant, then you are on this trajectory. And we are saying that if the yields remain constant, and even though you bought the bond for 85 and then say you sell the bond for 86 over here, we do not call that a capital gain. We only have a capital gain if interest rates go down and you sell for something higher than this constant yield trajectory. That's one point. Another point is that between your initial investment and whenever you sell, for you to have a return equal to YTM, you need to reinvest your coupon payments at the YTM rate. If you can reinvest at higher rates, then your realized return will actually be higher than YTM. Okay, now we get into an area that students find confusing because there are so many different definitions of duration, but I'll try to make it relatively straightforward. The first high level point is this. So this applies to all measures of duration. The duration of a bond measures the sensitivity of the bond's full price, which means that we are including accrued interest, to changes in interest rates. There are 4 measures of duration that you need to learn here as part of your level 1 curriculum, and I'll give you a way of remembering them in order. The first thing you remember is Macaulay, then modified duration, then approximate modified duration, and effective duration. So remember it like this. M, so you have M, AM, and then we'll come to effective duration separately. So just remember MAM, right? 2 M's and then AM. So the first M is for Macaulay. That's where it all started. Then modified, and then approximate modified. All these are yield durations, and I'll talk about that distinction. But just remember MAM. Okay, so the 2 M's and then AM. Now let's go through the definitions. The first one is Macaulay duration, and this is the original definition of duration and named after the gentleman who came up with this definition, Macaulay. Macaulay duration is a weighted average of the time to receipt of the bond's promised payments, where the weights are the shares of the full price that correspond to each of the bond's promised future payments. So in other words, this is a weighted average of how long it takes to recover all your payments. We go through an example where we talk about this in detail, but I'm not covering that in this particular segment. There is also a complicated formula for Macaulay duration. If you want to be super diligent, you can learn that formula, but I think the probability of you being tested on that complicated formula is relatively low. But understand this concept, and later there will be another very important point related to Macaulay. I will emphasize that later. So this is Macaulay duration. Then from Macaulay duration we can come up with something called modified duration. Modified duration is equal to Macaulay duration over 1 plus R, and this is something that you must learn. So this is easy to remember. So Macaulay is the weighted average of the cash flows. Then modified duration is Macaulay duration over 1 plus R. Modified duration provides an estimate of the percentage price change for a bond given its yield to maturity. So at a given yield to maturity, if the modified duration is 2, then that is telling us that if there is a 1% change in yield, then there will be a 2% change in the price of the bond. You will sometimes see this term ANN mod dur. So this stands for annualized modified duration, and the assumption when you are given modified duration is that you are looking at an annualized number. So this relationship is also very important. Your percentage change in the full price is equal to minus annualized modified duration into change in yield, and the minus is there because if yield goes up, then the price will come down. So that's captured through the negative sign. So what have you learned? You have learned the basic definition of Macaulay duration, and you've learned modified duration, which is Macaulay over 1 plus R, and you've also understood the interpretation of modified duration. Then the next thing in our MAM scenario is approximate modified duration, and this is also very important. This formula you need to learn. Approximate modified duration is the price Negative means when the interest rate goes down. So PV minus is actually higher than PV plus. PV plus is when interest rates go up. So you do PV minus minus PV plus over 2 times delta Y. Delta Y is the change in yield on either side in decimal. And then times PV naught, that's the initial price. So if you are initially at this point, where let's say that the yield initially is 8% and PV naught initial price is 100, then you can shock the yield or increase the yield by, let's say, 10 basis points. 10 basis points means 0.1% or 0.001 in decimal. So that's what the delta Y will be. If you do that shock and you get a certain PV positive, so that will be given to you, for example. So you have the PV positive. And then what if interest rates are decreased by 10 basis points? Then you will have PV negative. So it is conceivable that you are given PV negative, you are given PV positive, you are given that delta Y is equal to 10 basis points, and you are given PV naught, which is the initial value, and you are asked to compute the approximate modified duration, and you just plug and play. The interpretation of approximate modified duration is that it is the slope of the tangent to this price yield curve at a particular point in time. And you can see that the tangent is obviously telling you about the sensitivity of changes in price to changes in YTM. But the key takeaway is that you must know this formula, and you must know that it is the slope of the tangent. Okay, now I'm going to emphasize a point related to yield duration. The 3 durations that I've talked about, the Macaulay modified and approximate modified, are all called yield durations because they look at the change in price based on the change in yield of that particular instrument. Right? When we talk about yield, we are talking about the yield of that particular bond. When you are dealing with bonds which have embedded options, so callable bonds, putable bonds, or mortgage-backed securities, which you will study in detail at level 2, these do not have well-defined yield to maturities. Hence, the yield duration measures, all these 3, the MAMs, they do not apply. We need to use something called the effective duration. And the effective duration is almost exactly the same as approximate modified duration, with one difference. Instead of using delta yield, we use delta curve. And delta curve refers to changes in the benchmark. So if the benchmark is LIBOR and LIBOR goes up by 10 basis points, that's what the delta curve stands for. So the curve is referring to a benchmark curve such as LIBOR. So that, other than that, the calculation is the same. From a testability perspective, if you get something that says that you need to find the duration of a bond with embedded options like a callable bond or putable bond, then do you use yield duration or curve duration?
Curve duration.
Then you use curve duration. That is the key point. Okay, now this is also important, properties of bond duration. The Macaulay and modified yield duration statistics for a traditional fixed rate bond are functions of the input variables. I'll emphasize what I think is more important here. So how does duration depend on coupon rate? In other words, how does interest rate sensitivity depend on coupon rate? Now, something we've talked about before, if the coupon rate is low, then the interest rate sensitivity or the duration is going to be high. Now, how do we see that in this picture over here? On the y-axis we have Macaulay duration, on the x-axis we have time to maturity. But if you take a particular time to maturity, let's say, along this dotted red line, the time to maturity, let's say, is the same, then this bond is a premium bond. Actually, for all these bonds, this is a premium bond, this is a discount bond, this is a zero coupon bond. Notice that as you move up, what's happening to the coupon rate? As you move up, the coupon rate is coming down, right? So the lowest coupon is with the zero coupon bond. So doesn't that have the highest? So that has the highest duration. A discount bond will have a coupon rate that is higher than the coupon rate of a premium. So notice that this relationship holds. The lower the coupon, the higher the duration. Okay, so interest rate sensitivity is high, which means duration is high. So that's the first point. How does duration depend on yield to maturity? So remember, duration is a measure of interest rate sensitivity. So if you look at this picture on the right, at high YTM, the sensitivity is less. At low YTM, sensitivity, so this is low YTM over here, this is high YTM. So at low YTM, the sensitivity is more. So the way we can put it is, if the yield is low, then the duration, which is the slope or the sensitivity, is high. So that's the second point. And then the third point is the number of periods to maturity. So if you think of time to maturity, notice that across the board, with the slight exception of a discount bond towards the end, but by and large, as time to maturity increases, what's happening to duration? It's also increasing. So at this stage, I'll not focus on the hump of the discount bond. That's a little bit advanced. Key point is that as time increases, then interest rate sensitivity increases. So obviously the interest rate sensitivity of a 10-year bond is going to be more than the interest rate sensitivity of a 1-year bond. So those are the main points. It also depends on the fraction of the period that has gone by, but I'll not cover that in this crash course. How do you come up with the duration of a bond portfolio? So you have a portfolio with, let's say, 5 bonds. Okay, so this is your portfolio. Either you can take the weighted average of time to receipt of the aggregate cash flows. So look at all the cash flows, and if you go back to the Macaulay definition, you can do this, take the weighted average of time to receipt, and these are the points that you can read. But the more common and practical approach is to take the weighted average of the individual bond durations that comprise the portfolio. So if you have these 5 bonds, let's say they are all there in equal percentages, so 20% each, and you have the durations of those 5 bonds, you just take the weighted average of the durations of those 5 bonds. This is commonly used in practice, easy to use as a measure of interest rate risk, more accurate as differences in YTM of bonds in portfolio become smaller, and assumes parallel shift in the yield curve. So at this stage, I'll just say that you learn these bullet points. Money duration of a bond and the price value of a basis point. So these are just things to remember. The money duration of a bond is a measure of the price change in units of currency in which the bond is denominated. Up till now, we've been talking about duration where we have a percent. So we say that a duration of 2 means that a 1% change in interest rate will result in a 2% change in bond price. When we talk about money duration, we are talking about changes in dollar value. So this is something you should remember. Money duration is equal to annualized modified duration into the full price. If you are given the Macaulay duration, then you will have to convert that Macaulay duration into the annual modified duration, and that's done in several examples in the curriculum. So if the value of a bond is 100 and annual modified duration is 2, then the money duration will be 200. And then change in price of the full, so this is the change in price of the bond, the full price, is minus money duration into change in yield. So if the yield changes by 1 basis points and your money duration is 200, then what is the change in price of the bond? So 1 basis point means 0.01%, which is the same as 0.0001. So for this particular bond, a 1 basis point change means how much change in the price of the bond? It's 200 into 0.0001. So what is that? So 200 and then 1, 2, 3, 4. So 1, 2, 3, 4. So 0.02. So that is the impact on the bond. So this is also the price value of a basis point. So what is the change in price of the bond if there is a 1 basis point change in interest rates? The other way to calculate the price value of a basis point is to say that you come up with PV minus. This is the price of the bond if interest rates go down by 1 basis points, minus PV plus, which is the price of the bond if interest rates go up by 1 basis point, divided by 2. We've already talked about convexity, but now we are going to highlight the fact that this is good. As in, we talked about the convexity effect, which showed that it's good, where we said that if interest rates go down by 1%, then the increase is more than the decrease when interest rates go up. So this is called the convexity effect. If you have bond A and bond B is more convex. So you as an investor, all else equal, will prefer bond B because convexity is your friend. This is the formula for approximate convexity. I think there is a small chance that you would be tested, but if you don't have much time and you don't learn this, it's not a huge big deal. You can still pass without learning this, but if you have time, then do go ahead and learn this. The next point is very important. So most probably on the exam, I think you will be given the number for convexity. So it will be a number like 45 or 50 or some number that is a measure of how convex a given curve is. Let's say that number is 50. Now, how do you use this? And this is important because we see it here, and the next reading on credit analysis also references this point. If you take the percentage change in the price of a bond and use the annualized modified duration concept, then we've talked about this earlier. Let's say that there is a 10 basis points change in yield. 10 basis points we've already calculated, that is 0.1%, which is 0.001 in decimal. So if interest rates go down by 10 basis points, then this part of the expression, annual modified duration into delta yield, will tell you the linear impact. It will tell you the impact assuming that tangent. So it will only bring you up to this point. Then the adjustment for the convexity comes from here. Notice because of convexity, the pure duration formula doesn't give you a good answer. It is still falling short. So to make up that adjustment, you need to then add half into the convexity adjustment into delta yield squared. And again, all the yields will be in decimal. All right. What if interest rates go up by 1%? Then the duration formula will give you here, and then you add the convexity adjustment. So whether interest rates go up or down, the convexity adjustment is always positive. It will always take you up. So that also shows that convexity is a good thing. Convexity is impacted by time to maturity, coupon rate, yield to maturity, and dispersion of cash flows. Just like we have approximate modified duration and then we have effective duration, similarly we have effective convexity. With the effective convexity, we look at the change in LIBOR or the curve. With your approximate convexity, we look at the change in yield of that particular instrument. So just remember the fact, whenever you see effective, be it duration or be it convexity, then you consider the reference rate. When you don't have effective in the name, then you look at the yield of the actual instrument. Interest rate characteristics of a callable and putable bond. So here in red, we have a regular straight bond, also called non-callable bond. Let's say that a bond is callable at 102% of par. Because of that call option, the price of the bond then is capped at 102. If you as an investor know that a bond is going to be or can be called back at 102, you will never pay more than 102 for that bond. So the bond price is capped at 102. What does that do to the interest rate sensitivity of the bond? The interest rate sensitivity goes down because you look over here, this bond now has negative convexity, which means that as interest rates go up, the price goes down but not by much. So when you have a callable bond, then the interest rate sensitivity comes down. When interest rates are very high, like over here, then there won't be much difference between a callable bond and non-callable bond, because at high rates, the probability of the bond being called is very low. With a putable bond, we have the following situation. Remember, the price of a putable bond is going to be more than the price of a comparable bond which is not putable. So in red, I have the non-putable bond, and then because of the put option, this bond which has the embedded put option, at any given yield, the price of the putable bond is more. And since the slope of the putable bond is less, we can say that the interest rate sensitivity is less. This is another important point related to Macaulay duration. With short-term investment horizons, we are primarily concerned with price risk. With longer-term horizons, we are concerned with price risk and reinvestment risk. And let me just make sure you understand these terms. If you buy a bond and interest rates suddenly go up, what will happen to the price of a bond? We've established that the price of the bond will come down. What will happen to your reinvested coupon income? So if you are holding the bond for a long time and now you can reinvest your money at a higher rate, that's a good thing. So when interest rates go up, price comes down, that's bad, but the reinvested coupon goes up, that's good. So two things happen, one good, one bad. So the question is, are you happy or not? So let's answer that question by considering a scenario. You have a 10-year 8% annual coupon bond, you buy it at a discount, you have a certain YTM, and let's say interest rates go down. Now whether you are happy or not depends on your investment horizon. If your investment horizon is 10 years, then the benefit that you get, or actually here interest rates go down, so reinvestment income will come down a lot. Why? Because originally the rates were high, now rates have gone down. So reinvestment income down a lot, but price will go up, but not as much. Overall, you are not happy. So in this particular situation, you are not happy because the reinvestment income went down more than the amount by which the price went up. If you have a short investment horizon of say 1 year, then you have a situation where investment income goes down a little, but the price goes up a lot. So if your investment horizon is short, then you are happy because the positive impact on the price is more than the negative impact on the reinvestment income. So there has to be a point where you are neutral, right? Neither happy nor sad. That is the Macaulay duration. So on this bond, if you calculate the Macaulay duration, you will come up with a number of 7. So if your investment horizon is 7 years, then the change in price and the change in the reinvestment income offset each other. So that is another interpretation of Macaulay. So if your investment horizon is, so if your Macaulay duration of 7 is less than the investment horizon of 10, then the coupon reinvestment risk dominates. If the two are equal, then the coupon reinvestment risk offsets the market price risk, and if the Macaulay duration is greater than the investment horizon, then the market price dominates. The definition of a duration gap is the Macaulay duration minus the investment horizon. So in the scenario where investment horizon is 1 year, the duration gap is equal to 6.
If you found this lecture helpful, then I'll be very grateful if you can do 3 things for me. Number 1, like this video. Number 2, like my Facebook page. And number 3, visit analystforum.com and there add my logo to your studying with profile. You can see this slide for help on how to do that. Thank you very much and good luck with your studies.